Okay, welcome to this final lecture in the short series on mathematical modeling of epidemiology. So this is, this last lecture in the series, and it's taken from chapter 4 of the type notes. So I call this chapter a workshop, this lecture, this chapter, because here I go through a worked example in detail. So in this recording, what I'm doing is I'm going through the worked example and I'm putting the relevant codes in a little repository on the website, Case Studies in Mathematical Modeling. Okay, so we start by looking at the provided data set. So if you're, the corresponding section in the type notes is 4.1. The data set that I talk through in this section, you can already download on the website. It's data1.csv. I have to confess these are synthetic data. So they're slightly made up, and we'll be fitting the model to the synthetic data. And this is just a first exercise in learning how to do this. And if you do the main project, you'll be working on realistic data sets. Some of them will be the proper data sets from, for example, the COVID-19 outbreak in Ireland. Okay, anyway, here's the data set. It's given in CSV form, and I've also generated it in MATLAB form. And that can be read directly into my codes. So the codes I talk through are in MATLAB, and that's fine. You can rewrite these in any language you wish. You'll hopefully get the same answer. So anyway, you open the data file in CSV or in MATLAB and you plot. So you get the number of infections as a function of time, and you get the characteristic spike associated with an epidemic. There are two parameters that are really fixed and known for this problem. So big N, the population size, and the final time that we want to simulate. So these, for instance, are fixed here in SIR_solve.m. These are the parameters used to generate the simulation. So S init on 4.9 million, R init is 0, and the final time 100. Time is measured in days. So we're going to fit an SIR model to the data. Here are the equations. ds by dt equals minus beta over n si. di by dt is beta over n si minus gamma I. And dr by dt is gamma I. So n is known. Beta is going to be an unknown parameter that we have to estimate. Gamma is another unknown parameter. And another weird thing that's a bit different here is that we solve these equations starting at a time of minus t offset. This t offset is a third unknown parameter because we don't know who patient 0 is, when he was introduced to the population. So that uncertainty is accounted for in the existence of this third parameter, t offset. And I should say we're looking at proper SIR equations here. We're not scaling anything by S naught, for example. We're not looking at the reduced equation for U. We're looking at the full 3-equation model. And as I said, the simulations are started at this unknown initial time of minus t offset. At the initial time, patient 0 is introduced. So the number of infectious individuals at time minus t offset is 1. And number of susceptibles is n minus 1, and there's nobody recovered at the very beginning of the outbreak. So there are 3 fitting parameters, beta, gamma, and t offset. So we then propose a cost function, which depends on the 3 parameters, beta, gamma, and t offset. And the cost function is defined as the distance squared between the model and the data. So in this, how do you measure the distance? It's trial and error. You could do least squares, but it doesn't really work. So in this particular kind of approach, I play around with the cost function. And so the cost function I'm proposing is the least squares of the log. So I look at the log of the model minus the log of the data, and I'm fitting a curve for the number of infectious individuals. So log I model minus log I data. So here in this cost function in equation 3, Ti is the time in days. So the first day is I equals 0, corresponding to a time of minus T offset. And the last day is a time T. And actually, this is not quite correct. The data only start at time 0, the first day, and T offset is kind of far back in time before day 0 from the first day. So the last day at T equals big T. Epsilon then here is just a small regularization parameter that I need to include, and it just avoids any possibility of computing log of 0. So the cost function 3 then is just minimized using numerical optimization. And in this example, I do it in MATLAB, but it can just as easily be done in R. And there are some nice examples on the web of R codes where they do the precisely this problem. They fit an SIR model to some data. So if you prefer R, I'd encourage you to do that Google search and to find the equivalent examples to the one I'm showing here. So yeah, we minimize this cost function in equation 3 using numerical optimization. The syntax for this is shown here, and the code is called getparams.m. So here I'm loading the initial data from data1.mat. I create a function handle to the MATLAB file. And so what I'm saying here is the cost function is called mycost.x, my cost, and it's a function of this argument x, which is beta gamma t offset. So when I call the function, I call it via a handle. And this is how I set up the handle. I need to make an initial guess for my parameters, so I just pick something that I think is reasonable. I put in bounds on the guess, lower bounds and upper bounds, and again, just values that I think are reasonable a priori. For instance, the rates can't go below 0. After that, I just specify some options to the optimizer, and then the optimizer is called fmincon. So I'm calling fmincon, which will optimize. It will find the min over x of j of x, where x is equal to the triple beta gamma t offset. So the optimizer fmincon is calling the cost function, minimizing the cost function. This is my initial guess. These are null arguments, lower bound, upper bound, and options. And when that's done, the solution is picked out, beta, gamma, and t offset. And so the optimal parameter values are given in this table in values in units of days. So beta is just over 1 per day. Gamma is just under 0.2 per day. And t offset is minus 2.7 days. Or I should say t offset is 2 days. And so the initial time of the simulation will be minus 2.7 days. And the graphical results here, and you can see with this particular choice of cost function, where I take the difference of the log, the difference squared of the log, I get really good agreement. So this is my SIR model fitted to the data. What I want to show you next is one of the few statistical tools that I have up my sleeve. It's how to do an error estimation on the parameters beta, gamma, and t offset using bootstrapping. So here, if you like, is the recipe for bootstrapping. What I'm going to do is I'm going to compute the residual. So the difference between the log of the data and the log of the model for each time I. And if you like, the residuals are like gold dust, because the residuals are samples that are drawn from the distribution, which describes the difference between the model and the data. So these residuals are true draws from the distribution of the model error. So these are like these numbers. If you have them, they're like gold dust. So I generate these residuals, or I compute them, and then I resample this vector of residuals with replacement. And this produces, well, a resampled residual R tilde. And with this R tilde, I generate a new, if you like, synthetic data set, which will be the model plus the resampled residual. And I then fit the SIR model to this new synthetic data set, and this gives me new estimated parameters, beta tilde, gamma tilde, and T offset tilde. And I repeat this process, and this gives me a whole ensemble of values at beta, gamma, and T offset, and I draw histograms of these ensembles. This is a computationally intensive task because I have to do the bootstrapping n bootstrap times, and each iteration of the bootstrap algorithm requires a nonlinear optimization, and each function call to fmincon involves solving the ODE solver. And to get fmincon to converge, I might need to do n typical iterations. So that's n typical ODE solves. So to do bootstrapping, when you're fitting the ODE model to the data, the number of ODE solves is n bootstrap times n typical. And we don't know n typical a priori. As I said, it's the number of function calls required for the optimization step to converge. From this example, n typical is around 30, and I've done n bootstrapping of 100, so you're talking about 3,000 ODE solves. And I also share with you the code to do the bootstrapping. And I show the results. So I have the histograms for beta, gamma, and T offset, and I take confidence intervals. So I take confidence intervals from the 2.5th and the 97.5th percentiles of the histograms, and that gives me my parameters, beta, gamma, and T offset, with upper and lower bounds taken from the confidence intervals. And I've just checked that these results don't change if you do n bootstrap equals 100 or 50. So these results are robust. So that's the end of this little workshop. And just to summarize what we've done so far, in these chapters, so chapters 3 and 4 of the type notes, we've introduced the basics of SIR modeling. And we've shown how to fit them to data. That's what's new in this workshop. Now, in the main projects that follow, if you do a project on epidemics, you'll be asked to look in a lot more detail at kind of more complex epidemic models. For example, an SEIR model, or maybe a model with age stratification. And I'll also show you some other ways of fitting the models to the available data. But I hope, and indeed I'm pretty confident, that these lectures give you the right tools and the right training to tackle these more complicated problems. And essentially the principles will remain the same as the ones you've encountered in these few lectures in this short series. So thank you very much for listening.